The first thing we need to do on this problem is check the conditions. In my class you might remember QQ straight enough, no outliers, the plot doesn't thicken. We are doing regression. So let's scroll down to the graph to look at it. Quantitative, quantitative, which I call QQ. If you're not in my class, probably call it quantitative condition. Both variables are quantitative. Definitely pass right here. If we had something like hair color or male, female, something like that, then we wouldn't pass the quantitative condition, but both of these are quantitative. We have straight enough. Does the line appear to be straight enough? Does it represent, does the data appear to be represented by a straight line? We're not actually looking at the points here, we're looking at the line, and if the data seems to be around it. Now, if there was a bend in the data like this, we wouldn't meet the straight enough condition. So does a straight line approximate the relationship in the data? And I'd say yes. I would say right here, this straight line does a good job. No outliers. So the question is, do we meet the no outlier condition? And the answer is no. Do we meet the no outlier condition? No. So when we say yes, we're saying yes, there are no outliers. But we can't say yes here. There is an outlier, a car that had very high horsepower and had high highway gas mileage. We would predict that car way lower. It's an outlier in our predictions. Finally, we have, does the plot thicken? And if you look around it, you want to see, you would usually look at the residual plot, which we want to look at down here. We could also look at the line. With this in mind, here's our outlier. You might say the plot thickens. What I would do is draw with your pencil around the data on the residual plot and see if it thickens. Now, if you notice, it's really only due to that point. If you move that point down, it's not really going to get thicker at any spot. It's pretty much the same length around. It's more of an outlier issue than the plot doesn't thicken. And a lot of times we might say the plot doesn't thicken because we want to say yes, the plot doesn't thicken. What this condition is that our predictions are just as good up here as they are up here. We don't want to see it get tight around one spot or get really far out in other spots. This is the condition of equal variance around the line, equal variation. We don't want to see variation tight in one spot where the line's predicting really well and then spread out in another. So if you were to say it violates it, you could draw around it and say that the points get thicker around the line. A lot of times though we look at the residual plot and you could draw around it here and say the points get thicker around the residual plot, the spread gets thicker, meaning it predicts worse down here because some of the predictions are further out and it's tighter in predictions here. But with this in mind, it's really only due to that one point, so you could go either way on this one, and if you justify your answer, you'll be fine. So once again, to justify your answer, I would probably draw around it and show that it doesn't get thicker, as in be like it's only one point, without that point it doesn't get thicker, or draw with that point and say, hey look, it gets thicker, the predictions down here are worse. We violate, the plot doesn't thicken. So now let's go to some interpretation, and I would write these down. So we're going to interpret the linear fit, which is the line that we have over here. Now the linear fit is y hat, predicted y, write this down, equals b naught, that looks like b subscript 0, b 0, minus, and it's not always a minus, it can be a plus, b1, and that's b subscript 1, times x, which is the x variable. This is in your notes too, but make sure you can understand what the equation is. That says predicted y equals y-intercept plus the slope times the x variable. So let's go ahead and interpret the y-intercept right here. The y-intercept would state that when x is equal to 0, you can write this down too, to interpret the y-intercept, when x is equal to 0, we would expect, on average, highway gas mileage, y, to equal b naught, When x is equal to 0, let's click over them again. When x is equal to 0, we would expect y, highway gas mileage, to equal b naught. And if you notice, when x is equal to 0, let's trace over here. We would expect highway gas mileage to be equal about 44. If you notice, that's up here. That makes sense. That looks good to me. We go down to where x might equal 0, we trace up where the line would be, and that looks to be about 44. So once again, when x is equal to 0, we expect y to be equal to b naught. So make sure you have that written down and you can plug in the x and the y in the number. If you also notice, your intercept is down here. So we do have the intercept right here for the model. So this would be b naught, and B1. Now let's interpret the slope. I'm going to say it in the general form first and go ahead and write it down. For each 1 unit increase in x, we expect y to increase by B1. For each 1 unit increase in x, we expect y to increase by B1. So let's fill this in right here. For each 1 unit increase in horsepower, we expect highway gas mileage to decrease by 0.0691049 miles per gallon. So with that in mind, you notice that the highway mileage per gallon is going down as horsepower goes up. Horsepower goes up to 300 and the highway mileage is way down. Now, I did say increase to start. That's our general form right there. We do need to look at the sign right here and see if the slope is negative. So that would make it a decrease. So once again, for each 1 unit increase in x, if you notice, when x goes from 0 to 1, what happens? If it's 0, well, we're actually at the y-intercept. Just remove this right here and solve the equation with 0. When x equals 0, that's what y is. Now when we increase x to 1, we're going to subtract this amount. So for each 1 unit increase in x, when x goes from 0 to 1, this goes down, as in highway gas mileage. You notice the line does that. It has a very slow decline, because this is going up by hundreds, and this is only going down by tens, or 5s and 10s. So with this in mind, the model right here is actually the slope. And is the slope significant? On the very edge of my page, you will notice this. And I'm going to scoot this over a tiny bit here. You will notice the jump has starred the output. It's very important we look at the horsepower because the model here is the slope. Both of these test whether to see either of these is equal to 0. Does it really matter if the intercept is equal to 0? Well, that doesn't really matter to us. We want to know if the slope is actually significant, if this line's slope is actually telling us something. And the answer is yes, because the null hypothesis would be that the slope is equal to 0. The alternative is it's not equal to 0. So in this case, we reject the null. And if you're wondering when to reject the null, it's anytime there's a star on the jump output. It'll always star things below 0.05. We reject when the p-value is below 0.05, and here we have evidence to reject the null. One last thing with this output, we have r squared. R squared is always in the general form. You can go ahead and write this down if you like. Blank percent of the variation in y is explained by x. Blank percent of the variation in y is explained by x. So here we are. 45.2% of the variation in highway gas mileage is explained by horsepower. Good deal. Residual plot. So there's the slope, and there's talk about the slope. There's the intercept, talk about the intercept. So a lot of people on this problem had trouble when you take r squared and turn it back into correlation. You need to look at the slope or the graph itself and see if the graph itself is negative or going negative. So r squared right here, and when we square root it, remember it's a plus or minus number. So how do you know it's plus or minus? Look at the graph or look at the slope. Both of those indicate to you that the correlation is negative, because when horsepower goes up, when horsepower goes up, highway gas mileage goes down. Definitely negative correlation right there. Using the regression equation, estimate the gas mileage for a car that has 415 as horsepower. For this, we can simply plug in the number into the equation. We have our y hat equals b naught minus b1x, and right here we have the x variable right here, and we get the predicted y. A follow-up question could be, this car actually gets, its horsepower is actually 20. So, its highway gas mileage is actually 20. Go ahead and solve for its residual. So if it said its highway gas mileage is actually 20, what's the residual? The residual is always, and I give the residual RAP. Its RAP stands for residual equals actual minus predicted. So what is its actual? Is its actual 20 or 13? And think for a moment with what I said. May I rewind the video? In this instance, 20 is the actual and 13.2 is the predicted, hence y hat is the predicted y. So if we do actual minus predicted, 20 minus 13.2. If you think about that, it's actually higher. So we'd be up here at 20 or so, and the 13.2 is the line down here. So if you have a point at 20, I'm way above, sorry about that, 20 is off this graph. you have a point at 20 and the line's predicting 13, so the line would go down here. You're above the line, meaning a positive residual, and you can see that. This point up here has an actual of maybe 36, and the line is predicting somewhere around 25, so its residual is like 11 or 12. Actual minus predicted equals residual. We'll look at an easy one right here. You can think about what's the residual for this point right here. What is its residual? Its actual is 40 maybe, as predicted is 35. Actual minus predicted, its residual is 5. In other words, if you put a straight line right here, its distance to the line would be 5. That's what a residual is, the up and down distance to the line from the point. Basically, how far we are off in our prediction. We are getting near the end of this problem as I scroll down too quickly again. Would you expect this prediction to be you made in part 5 to be accurate? Give a brief explanation. And this is the problem. We noticed it when I went back up to the graph. It is an example of extrapolation. Extrapolation is going outside of the X space on your model. This is the X space down here. The X space only goes to where you have data. So the X space on our model, and I always say extrapolation, we don't want to make predictions below about 145, and we don't want to make predictions above about 310 or so. It's hard to tell exactly where that's at, but you only really know what the model does here, because you're eventually going to get negative predictions here. If you have a car with 1,000 horsepower, the line's going to go negative. So something's going to probably change here. We're extrapolating this model, putting it out further than it belongs. So that is an example of extrapolation. Once again, making predictions further out on the X space than your model is actually contained in. Sometimes this is called the scope of the model. The scope of the model is the X space for which we can make predictions. So we don't want to exceed the scope, or else we've extrapolated from the model things that we shouldn't get. I think that does it. I'm trying to think if there's anything else super important to say to you guys about these problems. With regression, just be able to handle, I think this is a good example problem, being able to read the output, remember QQ straight enough, no outliers, the plot doesn't thicken. Be able to interpret all this output, and you should be good. Good luck.